bit late because the matter was not ready. Yesterday I was very busy. Today, first of all, somebody was having some doubts. They called me. Can you tell what is the doubt so that first I will clear the doubt and then proceed to today's lecture?
Excuse me, sir.
Yeah, please.
Sir, am I audible?
Yeah, I am audible. You are audible.
Sir, actually, in the previous class, you told about the low band pass filter that we have to set the limits explicitly. Sir, I didn't get that point, sir.
Band pass filter.
Yes, sir.
So regarding which portion you are telling?
Sir, like you told that there are multiple integrals and we set the limits explicitly, the voltage supply limit.
Okay, voltage supply limits. You are talking about speed or characteristics of motor, right?
No, sir, like about the saturation and integral.
Saturation of the integrator.
Yeah, integrator, sorry.
Okay, what I was telling is, say, integrator. First, I explained the physical implementation of integrator. It is normally implemented in electronic circuit as a capacitor in the feedback path of operation amplifier. And the integration will be stopped if the output of the op-amp is going towards saturation. So we have to stop the process of integration itself. That's why I defined it as an embedded limit within the integrator. I was telling you can give some 1 or 2 volt offset. Suppose supply voltage plus VCC and minus VCC, output cannot go towards the positive extreme and negative extreme. Always some offset is required. That depending on the device of the op-amp only, we can say what is the offset required. That only I mentioned. If it is a silicon-based device, germanium-based device, or FET-based device, different limits may come depending on the device offset. So to be on safe side, take 2 volt offset so that if supply voltage is plus or minus 15 volt, you put a integrated limit of plus or minus 13 volt. I think this is your doubt.
Yes, sir.
Okay, that's all. Anything else for anybody? Okay, so today we are taking the second part of our lecture for nonlinear system. Last class, some of you had done the step response for nonlinear system model of engine gimbal control system. Today I explained the second part of that. There's a frequency response of a nonlinear system. How we can experimentally evaluate. Before going to that, I would like to discuss a theory of linear time invariant system. What is the frequency response of that? After that, we will go to the nonlinear system. Okay. So as far as the linear system, first we consider only, we will consider now only stable linear system, or more specifically, linear time invariant stable system. Linear time invariant, all these terms are familiar to linear time invariant means coefficients are not changing, and it's a linear system that obeys superposition. Another is it is a stable system. So for linear time invariant system, you know that for stability, all the poles should be in the left half of S-plane. And that system you can call also as asymptotically stable system, because in linear system, stability itself means asymptotic stability. Asymptotic stability means the output tends to infinity, zero as t tends to infinity. So I am going to discuss the steady state sinusoidal response from G of j omega, where G of S is the transfer function of the linear time invariant system. So consider an LTI stable system with unit impulse response. gt with gs is equal to Laplace transform of gt. By the way, I have not sent you the course note. After this lecture, I will send you. Gs is equal to Laplace transform of gt, where gt is the unit impulse response. Now you are considering the response like this. Gt represents the system, and ut is equal to a sin omega t, where a is the amplitude, omega is the radian frequency, t is the time, and that is defined only for t greater than or equal to 0. And we take ut is equal to 0 for t less than 0. That is, we are considering only physical domain. That is, for t less than 0, we are not considering, always t greater than 0. Then the output yt is given by gt convolution ut. You know the convolution theorem. There is a Laplace transform of convolution of two signals is equal to product of their Laplace transform. And this can be expanded as 0 integral 0 to t g tau u t minus tau d tau. Normally you study convolution integral as 0 to infinity, but here one specific case, the input is 0 for t less than 0. That means if I am considering the limits beyond t, here the independent variable is tau. If tau is greater than t, what will happen? If tau is greater than t, t minus tau will become negative. The argument will go to negative, and u of that time will be 0. So there is no need to consider integration beyond t for the independent variable tau. So you can integral 0 to t g tau u t minus tau d tau is same as integral 0 to t g tau u t minus tau d tau. So the general convolution integral can be simplified like this. Now, on further simplification, you'll get yt is equal to, if we substitute instead of ut, the actual signal here. 0 to g tau a sin omega t minus tau. Ut minus tau is replaced by a sin omega t minus tau. D tau equals a imaginary part of 0 to t g tau e raised to j omega t minus tau d tau. Because you know that Euler's theorem say e raised to j theta is equal to cos theta plus j sin theta. So the imaginary part of e raised to j theta is nothing but sin theta. So I want to give an analytically better expression for sin omega t minus tau. That is nothing but imaginary part of e raised to j omega t minus tau. Now other things are real, g tau is real, so I can take the imaginary so-called functionality outside this total integral itself. Because if even though you take imaginary inside, g tau will be saying only in imaginary effect will come only for this particular exponent part. Thus we can have a compact expression for yt as a imaginary part of e raised to j omega t integral 0 to t g tau e raised to minus j omega tau d tau. Now we have assumed that system is stable, that is asymptotically stable for a linear system point of view. So you can say that gt tends to 0 as t tends to infinity. That is, if you excite the system with the unit impulse command, the transients will settle down towards 0 as t tends to infinity. That is another way of defining stable system. If you disturb it, it will come back to its original state as t tends to infinity. Thus, using this property, we can define a time called TSS. That is, let us define a time called steady state time, T suffix SS, such that beyond the steady state time, if you integrate this part, that is integral 0 to, that is, I am going to take integral for the entire infinite interval, 0 to infinity. Okay. And integral 0 to infinity, I am splitting into two parts. One is 0 to TSS, another part is T integral from TSS to infinity. It is 0 to TSS and then TSS to infinity. And if you compare these two parts of integral 0 to TSS g tau e raised to minus j omega tau d tau, you can consider much higher than integral TSS to infinity g tau e raised to minus j omega tau d tau, provided gt tends to 0 as t tends to infinity. This is making use of the stability. What I mean is, after a sufficiently long time, there won't be any significant transients. That's a meaning. So if you integrate the transients beyond that steady state time, the significantly larger time, the integral itself will be negligible compared to the integral up to that time. So that you can make this assumption, integral 0 to TSS g tau e raised to minus j omega tau d tau is almost equal to 0 to infinity g tau e raised to minus j omega tau d tau, which is equal to g of j omega. You know the expansion for Laplace transform. Laplace transform is integral 0 to infinity gt e raised to minus st dt. Now, t is represented to replaced throughout by tau, and s is replaced by j omega. So you will get, this is nothing but g of j omega. If anybody has any this explanation, you can ask. Otherwise, I will go to the next slide. Okay, hope that all of you understood. Otherwise, you can ask later also in the next class. Now, so what we, based on the previous explanation, you have defined a time called steady state time TSS in all practical.
So,
pardon?
So can you go to the previous slide? So that integral AIM e to power minus e to power j omega t integration 0 to t is your tau. So yeah, this one only. So the infinity expression, there is no t function now, so it will directly be into t. I mean, it is only a function of tau now, so it can directly be integrated.
Yeah, it's a function. That's why I can erase j omega t outside. You can integrate.
No, so it is directly integrable. No, it is only a function of tau, not t time, that is. And tau is a constant.
Yeah.
Hello?
Who told tau is a constant? Here see that explanation for this expression for convolution integral. So I am directly taking, this is a generally up to here. Integration is with respect to tau only. Tau is a variable, not a constant. Tau is not a constant. You might have confused with some time constant, something like that. Here it's variable. Okay. All right. Okay. Now for time t greater than TSS, that is that so-called defined steady state time, we can approximate yt as yt is equal to a imaginary e raised to j omega t g of j omega. How we approximate this? The previous slide says this was our previous expression, yt is equal to a imaginary e raised to j omega. Now this particular part, that is integral 0 to t g tau, we found that it is if time t is greater than TSS, you can replace this by t can be replaced by infinity for all practical purpose, and hence the entire thing can be replaced by g of j omega. So I have substituted g of j omega instead of this for t greater than TS, for all t greater than TSS. So A imaginary e raised j omega t into g of j omega. Now, g of j omega is a complex number. So you can always say g of j omega is equal to m omega into e raised to minus j theta omega. That is the magnitude argument form where m omega is the magnitude of g omega and theta omega is the minus of the argument of g of j omega. I have unnecessarily made a minus and minus here. For understanding, you can replace by plus plus, but the purpose is I explicitly define theta omega as the phase lag instead of phase lead, because in all physical system and normally we see phase lag. So I define in the magnitude argument form the argument as a lagged phase instead of a normal lead phase. That's the only purpose behind this. So for t greater than TSS, you can say yt is equal to A imaginary. I'm substituting for g of j omega here. E raised j omega t m omega e raised to minus j theta omega d omega. And m omega is a real number, so you can take it outside. A imaginary of e j omega t minus theta omega. So now I removed that imaginary because imaginary part of e raised to j omega t minus theta omega is nothing but sine of omega t minus theta omega. Thus, I get an expression for yt for a LTI stable system for t greater than sufficiently large time TSS. Output is A into m omega sine omega t minus theta. Now I am drawing it, what I have done. This is the command, A sine omega t, we are giving to an LTI system. Now I am plotting the output versus input. Only difference, I have changed the independent axis t to omega t. Omega is a constant here for a particular frequency. And initial portion, that is portion of time less than TSS, I put it dotted. So for time greater than or equal to TSS, so the axis start with omega TSS. Here also start with omega TSS. Omega t, it is actually phase sine. This is the command, A sine omega t, and the output is what? A into m omega is the amplitude. Here lambda is equal to A into m omega, and its phase is lagging with respect to the command. Say this is the command. Theta omega is the phase lag. That's why I specifically put minus theta omega here, so that here I can say a positive theta omega. Theta omega is a phase lag with respect to the command. So if you give input A sine omega t to an LTI stable system after settling down of all the transients, the steady state output you can get like this. This gives a practical method to find out m omega and theta omega. What you have to do is you take the system as I have shown here, subject it to A sine omega t for t greater than or equal to 0, wait for sufficient time so that all the transients settle down, then plot yt in an oscilloscope. Yt versus the input. Two traces can be there. One is the input, another is the output. Then compare the zero crossing point of the output with respect to input. Find out the phase difference. That is theta omega. And find out the amplitude ratio. And that is m omega amplitude ratio. So thus having found out m omega and theta omega, what is gj omega? Gj omega is nothing but m omega e raised to minus j theta omega. This provides a practical means to find out the sinusoidal frequency response g of j omega. Once we know g of j omega as an expression in rational polynomial form, replace all j omega by s, you will directly get Laplace transform. So this is an experimental method to find out Laplace transform of an LTI stable system.
Sir,
Any doubt you can ask?
sir, in output, the transient behavior will be till omega TSS plus theta.
Can you repeat once again?
Yes, sir. Hello.
I can hear.
In the output graph, will the transient behavior will be till omega TSS plus theta omega?
Yeah, here the transients will all settle down prior to omega TSS or
In the
TSS.
output also.
Yeah, input there is no transient, output only is having transients. So assume that system is asymptotically stable. So if you wait for sufficient time, the output transients all will settle down to zero and output will contain only the forced component corresponding to the input command signal. So this is a pure sine wave having single frequency omega. Okay.
Okay.
Single sine wave, single frequency. That is, if transients will have other components like damped oscillation frequency, etc., all such things will, that the natural frequency, everything will settle down, only the forced component will be there. Okay.
Yes, sir.
Okay. Now our purpose is to move to a nonlinear system. Now we are talking about frequency response of nonlinear system. So we have to determination of m omega and theta omega for an asymptotically stable nonlinear system. That is, given a nonlinear system, if we excite with a unit impulse command, its output also will go towards zero as t tends to infinity. In such a case, how we will find out the frequency response? The only thing is that Laplace transform is not applicable here. But the theory we developed here, now this is independent of Laplace transform. It is a pure experimental theory. We are giving a sinusoidal command. Wait for sufficient time so that all transients settle. Then take the output by input. But here, nonlinear system, output is not a pure sine wave. You know that nonlinearity itself means if you inject a sine omega t, output will contain many components. One component is DC component, some average value can be there, due to some offset in the output. Another is components due to the first harmonic, that is having the same frequency of omega, A1 cos omega t plus B1 sine omega t. This B1 sine omega t is in phase with A sine omega t, whereas A1 cos omega t is in quadrature with A sine omega t. Then going to the second harmonic, A2 sine 2 omega t, B2 sine, cos 2 omega t and sine 2 omega t. The second harmonic comes. If you have to extend the concept of frequency response, we have to consider only the fundamental harmonic, because nonlinearity means definitely other parts will be there, offset will be there, harmonics will be there, but direct extension of frequency response is only with respect to the same frequency component. So there is a need to extract the fundamental component out of the complex components in the output. So what we do is we have to go for Fourier series expansion for the output, and assuming t is 2 pi by omega, the period of sinusoidal command, here A sine omega t. So t is capital T is equal to 2 pi by omega. You have the expression, you know the general equation for Fourier series. So A1 is given by 2 by t integral 0 to t yt cos 2 pi t by capital T dt is equal to 2 by t integral 0 to t yt cos omega t, because 2 pi by t is nothing but omega t dt. Similarly, B1 is equal to 2 by t integral 0 to t yt sine omega t dt. Thus, for a sinusoidal command of A sine omega t, the amplitude of the first harmonic is square root of A1 square plus B1 square. We have to take this. hence m of omega is equal to magnitude of g of j omega. It's given by output amplitude of the first harmonic output, square root of a1 square b1 square divided by the input command amplitude, or in logarithmic dB decibel value 20 log to the base 10, m omega is equal to 20 log to the base 10 a1 square plus b1 square by a square. I remove the square root, and so because of this squaring operation, this will be a square, so that both will be equal. And I am going to give you some programs for this in the lab class, how we can find it out. And the phase component is obtained how? The in-phase component of the output U is equal to A sin omega t is B1 sin omega t, and quadrature component is A1 cos omega t. Coming to the previous slide, you can see that. You are subjecting the input A sin omega t, the in-phase component that is having the same frequency omega and the same sinusoid, sin omega t here, sin omega t. So in-phase component amplitude is B1 and out-of-phase component amplitude is A1. So the argument is normally tan inverse of quadrature component by in-phase component, that is tan inverse of A1 by B1. That's what I have written here. Theta is equal to tan inverse of A1 by B1. A1 by B1, and we have to get the 4-quadrant tan inverse. In MATLAB, there is a function called et tan 2, where you can define et tan 2 is equal to quadrature component bar B1. That is in radian. So multiplying by 180 by pi, you will get in degree. So this is the theory for today's class, and the frequency. What we are going to do is frequency response of linear dynamics is independent of input command amplitude, but the frequency response of nonlinear system is a function of input command amplitude. That you should remember. And this can be evaluated by taking the ratio of the amplitude of fundamental harmonic system output to the input sinusoidal command amplitude and the phase lag of fundamental harmonic system output with respect to input sinusoidal command. And a MATLAB program is developed to carry out the above task. The first part is to generate a sinusoidal sweep command of the specified amplitude and frequency range. And the second part is to extract the fundamental harmonic amplitude ratio and phase lag. So today you will be doing that. Abhilash will be explaining the sinusoidal sweep command as well as the how the various programs in MATLAB, DPFA, etc. will be working. And any doubts I will clear in the next class. Okay, I will send you the course note now. Any doubts so far?
Sir, will you be taking class in the afternoon today?
Pardon?
Will you be taking class today afternoon, or only Abhilash sir?
Abhilash will be taking. Abhilash will be taking. No theory class, only lab class will be there. As per the Abhilash, you can touch with
Okay,
Abhilash.
sir.
Abhilash, what is the schedule today?
Second batch will be.
Second batch. Okay. Okay. Sorry.
Oh, sorry. First.
Sir, you told that the frequency response of the linear system is independent of the input command amplitude. But the response amplitude is m into a, right? So it depends on the amplitude.
Now, say for linear system, A is immaterial. Whatever A, you will get the same frequency response. The same value for m omega and theta omega. But
okay.
nonlinear system, m omega is a function of A amplitude. Theta omega is also a function of the command amplitude. That is the meaning of nonlinear system, you know.
Okay.
Superposition theorem is not applicable there. Okay, time is over. I will clear any doubts, outstanding doubts in next class. Okay. Okay. So.